Hello, this is FlippedHarber for Physics. In this video we'll go over the practice problems on page 181, numbers 12 through 14. In number 12 it says, suppose that the satellite in example problem 2 is moved to an orbit that is 24 kilometers larger in radius than its previous orbit. What would its speed be? Is this faster or slower than the previous speed? Now the first thing we need to figure out is what the radius actually will be that we'll plug into our equation. So I found the radius from example problem 2 and I added 24 kilometers. Now remember, the radius should be plugged in meters, and it was in example problem 2. I need to make sure that I'm adding 24,000 meters to this. So this is what I'm going to plug in for the radius. Now we're going to be trying to solve for speed, so we'll use this equation that comes to us from the section. The speed is equal to the square root of big G, which is the gravitational constant of the universe, times the mass of the Earth in this case, divided by that orbital radius. Remember, big G doesn't change, 6.67 times 10 to the negative 11th, and the mass that you're always plugging into these equations is the mass of the object that's being orbited. In this case, it's a satellite that is orbiting the Earth, so we need to make sure that we plug in the mass for the Earth in the equation. So this is what it looks like when we plug in our numbers. And what we end up with is a speed of 7.75 times 10 to the third meters per second. Now it's pretty obvious how to answer whether it's faster or slower, just compare it to the previous speed. But whenever we move an object to a larger orbital radius, it always slows down because it doesn't have to travel as fast in order to meet all the conditions of being in a circular orbit. So we move something out in radius, it will be moving slower. So this object is moving slower than the object was when it was closer to the Earth. Okay, let's move on to number 13. It says use Newton's thought experiment on the motion of a satellite to solve the following. Calculate the speed of a satellite shot from a cannon must have to orbit the Earth 150 kilometers above its surface. How long in seconds and minutes would it take for the satellite to complete one orbit and return to the cannon? So if you remember from the reading that Newton thought about putting a cannon at the top of a very tall mountain. If you shot it a long way, it would follow this parabolic path and it would get closer and closer to kind of like the edge of the Earth. And his idea was that if you shot it fast enough, that the Earth, the curve of the Earth is quote-unquote falling as fast as the cannonball is. So eventually it's going to come right around the back and hit the back of the cannon. And that's exactly what we're talking about here. So we're going to have to figure out our radius by taking 150 kilometers, that's 150,000 meters, and adding it to the radius of the Earth. So let's take a look at calculating the speed first. As I said, we have to find the orbital radius. That's the radius of the Earth plus the 150 kilometers. Don't forget that these r's that we're plugging in are center to center distances. So the center of the Earth to the center of this cannonball. Big G, gravitational constant of the universe. The mass, again, this cannonball is quote-unquote orbiting the Earth, so we're plugging in the mass of the Earth. And we see that it needs to be moving at 7.8 times 10 to the third meters per second. Now, how long in seconds and minutes would it take for the satellite to complete one orbit? So we're solving for t in this case, and here's our equation. We're going to need that radius again. We're going to need big G, and we're going to need the mass of the Earth. Getting plugged in very, very different this time. Here's how it looks with all the numbers plugged in. We type it into our calculator and we get 5,254. Now that is the orbital time in seconds. Divide by 60 to change that to minutes, we find out that it's 88 minutes. So if we were to actually be up on a mountain that's 150 kilometers tall, if we fired a cannon at the appropriate speed, 88 minutes later it's actually going to hit the back of the cannon. Okay, so number 14, it says use the data for Mercury in table 7, that's supposed to be 7-1 on page 173 to find the following. Again, we want to find the speed of a satellite that is in orbit 260 kilometers above Mercury's surface. So again, we're going to have to find the orbital radius. and we want to find the period for that satellite. So let's start with this question about the speed. Again, we'll use this equation, but notice the m, the mass has changed. It's no longer the mass of the Earth. This is a satellite orbiting Mercury. So that's one of those things that I need to look up in that table, is the mass for Mercury. Big G, don't need to look it up in a table. It's 6.67 times 10 to the negative 11th everywhere in the universe. That's why it's a universal constant. The radius that I found is 2.7 times 10 to the 6th. Again, that's the radius for Mercury, and then add 260 kilometers. Plugging it all in, this satellite needs to have an orbital speed of 2.86 times 10 to the 3rd meters per second. Any slower, and it's going to basically fall back to the planet. Any faster, and it's going to kind of spiral out and find a different place to orbit, or it's just going to leave. Okay, so let's find the period of this satellite. Okay, here's our equation again. I made that appropriate change to the mass also. Remember, we want to use the mass for Mercury from that table. So we plug everything in. It's going to look like this. And we get 5,941 seconds. Now again, standard unit for time, including this, is in seconds. If we wanted that in minutes, we divide by 60. It's 99.0 minutes. Divide by 60 again, it's going to give us hours, 1.65 hours. Okay, that's it. So I'll see you in class, and I'll see you online.